Right, hopefully we're back again and we're live. You might have just seen a bit of me. We weren't quite sure it was working at that point, so we cut it. We've gone back on. We're definitely live now. I've been given the nod, so we'll go ahead. This is our P1 live exam stream. Just before the exam obviously tomorrow afternoon. This is going to go through all the topics you need to know for that exam. Hopefully you'll be doing lots of revision anyway, and this will just be a refresher. If you want the notes, you should be able to download them from the Folkestone Academy website, get those and see them. If you can't see them on the board here, we'll also try to put the link in the description as well to the video. Just to let you know, the email address is contactscience@folkestoneacademy.com. If you have a question, please do email in. We'll try to make sure it's working and you get the full answer to your question. I know we had a few technical problems last time. We'll try to stay on top of that and make sure that you get the answer to your questions. Please do email in. If it's a quick question, we will respond to it immediately. We've had a wide range of views and hopefully you're enjoying this and gaining the most, and a lot of positive feedback that it's really helping you. So that's why we're doing it, and best of luck with that exam tomorrow. I'm going to say that now because I'm actually going to go because we've got a guest host today. Mr. Pritchard's going to be taking us through the physics we need for the exam. So I'll be on the email, so if you have any questions they can come through to me and I'll be able to pass them on to him to maybe be answered. And also I might answer over email as well, and Miss Walker will be there too to respond to those emails. So best of luck to you tomorrow. I'm sure I'll see you tomorrow morning when we will be in. Otherwise I'll hand over to Mr. Pritchard to take you through P1.
Alright, finally, my big break. Thank you, Mr. K, for this opportunity. I finally made it to the top. Okay, yeah, alright, P1, physics. Before I forget, Barrett, here's your shout out, you better be watching. Okay, so, first thing we're going to talk about is potential energy. Got to start the timer. Yeah, so potential energy. When an object is raised or stretched, okay, you're storing energy. So, this marker pen, as I raise it, it's now storing potential energy. I would call this gravitational potential energy. Also, okay, elastic band, as I pull it or stretch it, it's now storing potential energy, and I potentially could hit Mr. Cave off camera here.
Ow.
Yeah, so we call this potential energy, and there's elastic potential energy and gravitational potential energy, which I was just going over. So to calculate change in potential energy, we can calculate the change in gravitational potential energy by using the equation. Gravitational potential energy is mass times gravitational field strength times height. Okay, and take note of the units that we use. And to know gravitational field strength for Earth, it's generally, you could say 10 newtons per kilogram, but 9.8 newtons per kilogram would be great if you're a star. As for the equations, just like in prior live feeds, not going to go over too many equations for the sake of time. So it's a matter of you getting some practice, find some practice equations and work them out. Okay. The other important one is kinetic energy. Okay. Elastic potential energy. And when you use the energy, you use this equation, elastic potential energy equation. It's half times the spring constant. Okay, times extension squared. So that's another equation that may come up, and that's the two types of equations for potential energy. Okay, so just like you guys doing exams, like a little bit of a nerve, just let me smooth it out. Okay, I'll get through this. Alright, so now, transferring energy. Major thing, transferring energy. There's many ways we can transfer energy or transfer it to different stores of energy. I didn't make a list here. We got elastic and gravitational, we just talked about. Kinetic, electrical, thermal, vibrational, nuclear, and chemical are all places where we can store energy. So it's more useful to know where the energy is each time. Then we figure out how it's been transferred. Okay, so for example, I got a picture of this wind-up torch. And if I had that wind-up torch now, I would use the chemical energy that's in my body, and I would start turning the torch. This energy is transferring from me now into the battery. Okay, so it would become chemically stored in the battery. Now once I turn the light of torch on, it goes from chemical to electrical, in which case the light then comes on. And then the energy is transferred to the atmosphere through waves, or dissipates as heat. And that's where the energy would transfer, and we'd figure that out in the end. Same thing with a wind-up toy. I got my nice wind-up Shrek toy here. If I was to start winding him up, I'd be storing elastic potential energy, and then as I released it, that energy then would be transferred into kinetic energy, and this fantastic looking creature here would start walking across the desk, okay? And that would be the kinetic energy as it moved. And so kinetic energy, energy has to be transferred in order for things to move, to make things move. And the greater the mass of that object, or the speed of that object, the more energy that's going to be transferred into that energy's kinetic energy store. This is an equation that you have to memorize. I'm almost certain it's going to come up in one form or another in the exam. Okay, so kinetic energy is half the mass times velocity squared. And like all these equations, you have to understand that on the exam, generally when you have to use an equation, they're going to give you at least 2 of these units. Alright, and you work out the one that's missing, what they're asking for. Now it could be a 2-part question, where you might have to find the kinetic energy first, and in the second part you use that answer in the next part of the question. It's important for you to know that. Okay, we're doing good for time. So move on to work done and energy transferred. And as if you can't tell already, this physics is very equation heavy, okay? So there's going to be a lot of maths, which you might suspect. So work is only done by a force if the object moves. So in order for work to be done, the object has to move. So if I just hold this marker pen, I'm not doing any work. However, when I start to raise it above my head, now work is being done. So they might, even if a weightlifter is holding 100 kilos over his head and he's stationary, he's not actually doing any work. But as he's lifting it is when the work is being done. If the force is bigger, the object moves further, that's when more work is done. Equation, once again, I have in the bottom, which you guys should have access to these slides. So we got work done in power. So power is actually the rate of doing work. Okay, so it's how fast this work is done or how fast the energy is transferred. Therefore, a machine is more powerful than another machine. If it is more powerful, it can transfer more energy, or it does more work per second. That means something's more powerful than something else. So some more equations where power is equal to the work done in joules over time, or energy transferred over time. That's how we would calculate power in this instance. So that's another equation for you guys to familiarize yourselves with. Another big topic, which actually comes up twice in P1, is specific heat capacity. And what specific heat capacity is it takes more time to make some things hot than others. So I do have a picture of this beach here. And have you ever noticed that if you go to the beach, the sand gets much hotter than the water, quicker. Okay? The same amount of energy from the sun is hitting them both, but the sand gets much hotter. And the reason is because water has a much higher heat capacity than the sand. Okay? So it has a better capacity of taking in energy before it starts to heat up. And we can use this information. So we can use this specific heat capacity of water to find out what the heat capacity is of other objects, so other metals. And using this equation, which is equation for specific heat capacity, we have the change in thermal energy. Okay? So the mass times specific heat capacity times the change in temperature. And it might be written, you'll see it written in different ways. This would be the way it's probably going to come up on your exam. I'm not sure, Mr. K can help me. Are they going to be given this equation?
They're given that one on the equation.
Okay, you'll be given this one on the exam, so that's perfect. Yeah, and how can we use this? So you might see, they might bring up practicals. So investigating specific heat capacity, and one of the ones that's common is you'll have a beaker a beaker of water, and maybe we're testing copper. Okay, so they'll have the copper in the water, thermometer, and it might look something like this, and this is the copper. Now, the water they would have at 0 degrees. And while the copper is in there, that will bring the copper down to 0 degrees. Then they'd have another beaker with the water already at a set temperature. Okay, so it might be I'm trying to get the exact practical right here on my notes. Sorry. So the water would be say maybe 80 degrees. And we would transfer the copper over to this water and see how much the temperature changes. Because the heat is energy is going to transfer into the copper, and we can see how much has actually transferred out of the water into the copper. And then we'll be able to tell the heat capacity of the copper. And that's one of the practicals, or a way that we can investigate specific heat capacity. And you'll often find that on the exams, I've noticed over the past 3 years from the students taking them, they'll come after the exam's over saying, "But sir, we've never seen it done that way," or "I didn't know what this was talking about." What's important for you guys to understand is it's not so much the objects they're using. Find out what it is they're asking, and if you know that concept or that idea, that's what you need to talk about, and that's what you need to figure out. Okay, so then we got dissipation of energy. Okay, sometimes transfer of thermal energy is useful, but other times we may want to reduce this transfer of thermal energy. So obviously, if we're using an oven, thermal energy is useful. But in a light bulb, we don't really need a light bulb for heat. We just need it for light. So the ways that we can reduce heat loss or dissipation of thermal energy is lubrication. So this will reduce friction. So less energy is wasted as thermal energy. So if you reduce the friction, then you'll get less heat being generated and lost to the atmosphere. And also thermal insulation. So if you had a hot object, you can reduce it by surrounding it in insulation. For example, if you got your fish and chips and you want to take it home, usually we can wrap it up in something, and that keeps the heat inside. It slows it, what am I looking for? It decreases the rate at which it will transfer out of your fish and chips. So, talking about homes, I got this image here. So this is an infrared image, and it actually shows thermal energy transferring out of this home. And you can see specific spots where it transfers out more than others. So in the roofs, in the windows, you can see around the edge of the door here. So that's a lot of heat loss coming from this home. And specific places where we lose the most heat from our homes, you see in this diagram here, is a lot is lost from the walls and from the ceiling. Okay, windows, doors, and even drafts. So we got to figure out ways of reducing. If we want to reduce heat loss, then we would need to do things such as maybe put in double glazing windows. So on this side, we have single glazing windows with a lot of heat loss. We install the double glazing, and right away, we've minimized heat loss from this home. So you then save, that's where you save money and energy. And when we're talking about efficiency, okay, so no energy transfer is 100% efficient. Energy is always wasted, so always. I would argue, or I wouldn't argue, I would say most energy is wasted through heat and sound. Okay, so if you got an appliance that's really loud, maybe that dryer, that tumble dryer that's always rocking around, sometimes moving across the room, that's not very efficient. Okay? Just like cars. I had a discussion in lesson where I was talking about the efficiency of cars, and some kids were saying, well, this car is better than this one. I was like, yeah, you might consider that a better car or faster, but it's quite loud. So when it comes to fuel consumption, which is stored chemical energy, you're going to burn a lot more in a louder, faster car than you would in a fuel-efficient vehicle, which would be much quieter. So a Sankey diagram shows energy transferred in the process. Let's say that this Sankey diagram is for a light bulb. So electrical energy going in, so the total amount of energy going into this light bulb at first is 100 joules. 75 is used as light, but we're going to lose 25 as heat coming off of this light bulb. Alright, we need to work out how efficient this light bulb actually is. And we would do that by taking the total useful energy in and dividing it by the total energy. And you get how efficient something is. Now, nothing ever is totally 100% efficient, but I have read some things about MIT. It's a technical college, and they're currently working on a light bulb that's exceeding 100% efficiency. Because what they're doing is, the dissipation of energy that's leaving this light bulb, which generally spreads out too far for us to use again, they're finding a way to catch it and filter it back into the light bulb. So it's making a much more efficient light bulb, which is kind of cool. When it comes to generating electricity, there's a number of ways. Okay? In general, we sort them into renewable and non-renewable resources. So renewable, we have things like the sun, wind, okay? So water, which I like to group in as wave, tidal, and hydroelectric. We have geothermal, and we have things like biofuels, which is made from like plants, etc. The non-renewable, we have sources like coal, oil, gas, and nuclear fission is another one. So most of the time how it works is you put the heat energy, usually chemical energy stored in coal, gas. This is for fossil fuels. You put the coal or gas, we heat it up, and that's going to heat a boiler. Okay, so as the water moves, it's going to turn, or the steam moves, it's going to turn a turbine, and that turbine is going to power the generator. And that's where the electricity is going to come. So you do have a transfer of heat energy. It transfers into kinetic as it spins the turbines, and then kinetic as the generator moves and transfers it to electrical. Okay, so that's 3 energy transfers there just in a system like this. And if you look at, we have a Sankey diagram at the bottom also showing the efficiency of this. Okay, so even if we did that same 100 joules of energy, we've lost 20 joules to heat, 40 joules when the steam cools to water. Generator losses equates to 5 joules. So in the end, we're getting about 35 joules of electrical energy off of that initial 100. And we're talking about fossil fuels in particular. We have advantages and disadvantages that they might want you to discuss or compare. So advantages of fossil fuels, they're reliable. Okay? And gas has a particular quick startup time. And the infrastructure is already in place. So it's what we're already using. And we all know how people hate change. Disadvantages, however, is we're running out, releases carbon dioxide, and that's going to contribute to global warming. Yeah, that's a key term you always hear. And it releases sulfur dioxide, and that's what creates acid rain. So get to know advantages and disadvantages, because it could be a question where it asks you to compare renewable and non-renewable resources. Nuclear, so the reaction is nuclear fission, so the fuels are uranium and plutonium. And the advantages are, it doesn't produce carbon dioxide or sulfur dioxide, so that's some major advantages, and it actually produces a tremendous amount of energy. Okay, so nuclear is quite efficient in that matter. The disadvantages of course, are it's non-renewable, radioactive waste is produced, risk of accident, and it does have a long startup time, so if it were to shut down, it does take a while to get up and running again. I know from a lot of my students, whenever we bring up nuclear, they always refer to Chernobyl and that stuff, but I assure you, a lot of things went wrong that night for that to happen. Renewables, we have solar. So the advantage is it's renewable and it doesn't pollute, but it is expensive. Okay, it's inefficient and it only works during the day. Now these are things that many people are working on now to try and make this a cheaper energy alternative. Wind, it's the same thing. It is renewable, there's no polluting gases, but it's noisy, it's unsightly, and it's inconsistent. Okay, so it's inconsistent because it's not always windy. It's unsightly because some people don't want to look out over the horizon and just see hundreds of windmills. Okay? We have water, which I grouped into wave, tidal, and hydroelectric. So advantage is renewable, no polluting gases. You see a theme here, and it is reliable. However, these ones do destroy habitats, and it does need water nearby. And things like tidal, you have to rely on when the tides will be in, when the tides will be out, what's the water level. These are some advantages and disadvantages. So you get your head around being able to explain and think or compare if they give you some renewables, or maybe they're going to talk to you specifically about one of these and compare it to oil and gas. It could be any of these, alright? It's not always going to be exactly what you talked about in a lesson, but you do know the things you're looking for that would be an advantage. You know things that are a disadvantage. So use those in your answer no matter what it is they may bring up. And then we're going to talk about geothermal. Okay, it uses heat from under the earth. It still produces steam, and that does turn it'll turn a turbine, and that's going to be connected to the generator. So much like we've seen the power before with oil and gas. But it has no fuel costs. It is renewable, and no polluting gases. Disadvantage, it has to generally be in volcanic areas for it to work the best, most efficiently. So I believe Iceland use a lot of geothermal. Sarah's giving me the nod. Gave me that reassurance. Now, alright, so we got through that first part, and this is all of us getting amped up for the rest. Just look at this kid. Watch this. Yes, come on, physics! Everyone's laughing at me now. Okay, so, helpful info. I decided to put up this slide. You're going to get this. I'm not going to talk about it much, but I'm leaving it there for when you guys look at the slide yourself. I'll just get you some letters that they do use, because I remember when I was your age and I was doing this kind of thing, I'll be like, why are they using a Q for charge and an I for current and stuff like this? But I assure you for now, just accept that it is what it is. Alright, and try and learn it that way. So I put that slide up for a little bit of helpful info. Now, we're going to talk about electric current. So current is the flow of charge which is caused by millions of electrons passing through a component. Okay, so picture you got this wire, and we have millions of electrons are flowing through this wire, and that would be the charge. Or that would be the current, sorry. Charge, okay, is that current over a set amount of time. So a wire carries a current of 1.2 amps for 30 seconds. How much charge flows? So I would do that equation, okay? So charge is current over time. I would plug in the numbers that it's given me. So it's giving me 2 amps and seconds, so it's giving me a time. So 1.2 times 30 equals 36. And I put the units in for charge, which we looked at earlier, which is C. Okay, and that's coulombs. I was always calling it coulombs, but I found out that you pronounce it coulomb. Fair enough. Then we go into potential difference. Okay, so I am doing a few minor examples in this because it's going to help you see how my mind would work doing it. So it's the energy transferred for every unit of charge. Okay, and this is measured in volts. Okay, so potential difference is measured in volts. It is okay to say voltage, but you need to understand that the scientific word for it is potential difference. And it is V, so potential difference equals current times resistance. An example, what is the potential difference of a current of 2 amps and a resistance of 5 ohms? So once again, it's given me 2 numbers. So I know in my head, if I know this equation, I can plug those numbers somewhere in here. Okay? And amps is current, so we would go potential difference equals current times resistance. I'll fill in the 2 for the current, the 5 for the resistance, and I end up with 10 volts. Okay, so 10 volts of potential difference. That's another example. So any equations you get, I'll keep on reiterating this. they're generally always going to give you 2 bits of information to use. So look for those and then find out what it is they're actually asking, then use the equation that you know. So if we calculate the potential difference across a 5 ohm resistor when the current through it is 2 amps, really what I want you to understand is here, what is actually going on when I'm talking about potential difference, current and resistance. Because resistance, if you look at this is metal ions, they're all set in place. And if I send a current or a charge through that, these millions of electrons are coming through. And as they go through, they're actually hitting these metal ions. So they're hitting these metal ions that are in place, and as they do that, they're transferring a bit of energy to these metal ions. And the more they hit these metal ions start to vibrate, and then they start to heat up. And that is the resistance, and that's why things will get quite hot. So wires will light up. It's why a light bulb, a filament light bulb, actually gives off light. Okay, so all these electrons, as they hit these metal ions, they're transferring energy in. Those ions are gaining this energy and heating up, and then sometimes they heat up so much they emit this bright light. And that was a light bulb. So we can use all this information of resistance, current, and potential difference to answer a series of questions to find any of these. So once again, potential difference across a 5 ohm resistor when current through it is 2 amps. Well, if I know potential difference is current times resistance, I would fill in the current, 2, times the resistance, and I get my potential difference again, which is 10 volts. Where does all this information come into play? All the currents, potential difference, voltage, amps, well, it's in circuits, okay? And there's 2 types of circuits we're going to talk about. First one is a series circuit. So series circuits are when all the components in a circuit are connected, you can see here, in one continuous loop. If there's a break anywhere in the circuit, electricity will not be able to flow. So if I put a break anywhere in this circuit, the electricity will no longer flow. So if you look, this here is a switch open, so electricity will not flow at the moment. In a series circuit, the current is the same anywhere in a series circuit. So I can put the amp meter anywhere on this series circuit and it'll come up with the same reading. However, the potential difference supplied by the battery is shared between the components. Okay, so whatever voltage this battery is, it will share that potential difference between these 2 light bulbs here. So remember, in a series circuit, current stays the same, so amps will be the same no matter where I test it, but yet voltage will change. It will be shared amongst the components in this circuit. In a parallel circuit, if you notice the difference, parallel circuits are circuits which have more than one loop. If there's a break in one of the loops, electricity will still be able to flow. So if I had a break in the loop right here, if I remove this bulb, the electricity can still travel around this other path, and the other light bulb will light up. Likewise, if I remove this bulb and left this one in, electricity would travel, or the current would travel this way, and this light bulb will stay lit. This is where it's reversed to a series circuit because the current will be split between the branches. So the current's traveling along, so many will decide to come this way, so much of the current, and the rest of the current will go this way. It will be split amongst the branches. And the potential difference, so the voltage in each one of these components would stay the same. So if I had a 1.5 volt cell, 1.5 volts here, 1.5 volts here in each light. It wouldn't be split, whereas in a series circuit, that would be split. We're going to talk about mains electricity. So electricity supplied in the UK is an alternating current, 230 volts and 50 hertz. So the voltage of the current is determined using the height of the wave. So you would use the height of the wave to determine how much voltage the current is. And if you notice, this is an alternating current. Okay, so it will go back and forth. And that's generally what's supplied to homes in the UK. Okay, we're going to talk about resistors now. So there's different kinds of circuits, components that can go in a circuit. The one that we talk a lot about are resistors. okay, and different types of resistors. It's these graphs that you have to understand as well. An ohmic resistor at constant temperature, as you can tell, the current and potential difference are proportional. Okay, so if one goes up by 1, the other also increases by 1, and that's Ohm's law. So we have a fixed resistor, and we also have a variable resistor, and these are the symbols we have. A fixed resistor, like in the name, the resistance will be fixed. So whatever the resistance is when your resistor is, whatever ohms, that's the resistance. A variable resistor, however, is one that can be changed. Okay, so you can increase or decrease the resistance depending on what it is you need to do. And if we talk about different things, like earlier I was talking about the filament light bulb, okay, and how it lights up. So a light bulb eventually is affected by temperature, and its current will no longer be able to increase. Once this filament gets too hot, okay, it's going to emit this bright light. The current will no longer be able to travel any faster than it already is. Okay, so the current's already will be at its max. And as you can see on this graph, so as we do it, this is where it stops to increase. So it's going to stay at this current now in this filament light bulb until we turn it off, it cools down, or it just blows. Okay, the light bulb just goes. We also talk about a light-dependent resistor. Okay, so a light-dependent resistor is when the light shines on it. It has a high resistance in the dark, but resistance actually decreases when it's in the light. So you can get this slide. I'm not going to read all this out, but basically what it says is in the light there's reduction resistance, because in the dark there's no extra electrons. So in the light there's extra electrons being added, so therefore it helps increase or lower the resistance in the light. I think I mixed that up, didn't I? I got all confused with my words then. Okay, have a look at the slide. Okay, so basically what you need to know is in the dark resistance increases, in the light the resistance will decrease. Okay, that's in a light dependent resistor. For a thermistor, the symbol is this, okay? So if you look for a thermistor, this is the type of graph it's going to look like. It's actually the reverse of the filament lamp. It actually conducts more electricity when it's heated. So as we add heat, it's going to start conducting more electricity. So have a look at this. These are the graphs you've got to familiarize yourself with and know what they fit with and what's going on there. All this is useful for what we call the national grid. Okay, this is how we get power from a power station to our homes. Now the power coming from a power station, it needs to travel a long way. And it does that by using step-up transformers and step-down transformers. So in a step-up transformer, we increase the voltage. So as we increase the voltage, we actually reduce the current that's going to be traveling across the wires. And if we do that, there'll be less resistance, meaning we're going to lose less of that energy as heat. Okay, we'll lose less energy heat, it's going to be more efficient. So when it gets to our homes, however, we can't keep it at that voltage. Okay, it'd be too dangerous. It would probably blow up all your appliances. Okay? For example, when I came over from Canada, I had a beard trimmer and I plugged it in. It's only like 120 volts in Canada in the sockets, but here it's 230 and my trimmer just blew up in my hand. Okay, so trust me, the science checks out. We'll step down the voltage. Okay, we'll step down the voltage back down to 240, 230 volts. I think it's 230. Yeah, just so it's safe for our homes again. And the current will then increase. So what I want you to know is you increase the voltage, that decreases current, and then if we decrease the voltage, we re-increase the current. And this lowers the amount of energy loss. So there's going to be less energy loss from the power station to our homes by doing this method. One of the useful things, I don't know if you guys can remember doing this, hopefully you do, is watering a plug. Yeah, I had one on hand, but I'm not sure what I did with it. But if you look at this diagram, you have three main things, well, four main things I want to talk about, and that's the live wire. So the live wire carries a high potential difference into around the house, and the fuse is always connected to the live wire. And the reason that is, it's a safety feature. Okay, if there's a short or if too much power is coming in, the fuse will break. Okay, so the fuse will go out and that'll stop, I guess, any alternative damage that could happen. Neutral, the neutral wire, which you see right here, which is this blue wire. No current until the appliance is plugged in, and it provides a return route. Okay, so until the appliance is plugged in, this doesn't receive any current, and it gives a return route for the electricity if needed. So in and then back out. And then the earth wire is safety. So the earth wire is mainly there for safety. It's connected to the casing of the appliance. And it prevents the appliance itself from becoming charged. So if I was to plug in a kettle and it didn't have an earth wire and a shortage happened, there is a chance that the kettle itself could become charged, and as I grabbed it I would get an electric shock. But the earth wire is there to ground that out. So that charge will not happen. Power, okay, so power is measured in watts. So we always try to measure the power of things coming into our homes. Light bulbs, you'll often see like 60 watt light bulbs, 100 watt light bulbs. There are two equations for calculating it. So yeah, more equations, get ready. So power, like we talked about earlier, energy transfer over time. But power can also be current multiplied by the voltage. Okay, so that's always power, also power. It's just a couple more equations for you to learn. So, another nice little break for you. Who can do it? Look what the puppy's saying. He said, you can do it, okay? I think that's great. He's even giving you a wink. All right. Next we're going to talk about states of matter. Okay, we're doing for time. Alright, doing fun. So states of matter, the three states of matter you have to know. And we're always going to talk in terms of particles, obviously. It's solid, liquid, and gas. And if you can see the arrangement of the particles in each one of these, we have a solid, they're tightly packed in a neat pattern. Okay. For a liquid, they're still touching, but the way to show it, you can see, start to see some movement. Okay. You can start to see how they're starting to move apart from each other just a little bit. And then the gas spread out. Okay, so a gas will fill whatever container you put it in. Okay, liquid will take the shape of any container you put it in, and then a solid is the shape that it is. When we're talking about particles and states of matter, okay, we need to know a thing called, talk about a little bit about density. And what density of an object is its mass divided by its volume. Okay, so the mass of the object, we're going to divide it by the volume, and it usually comes up as, I say, for you guys, it looks like a little p. It's called po or fo, but I'll say p equals m over v. Little lowercase p, italicized it. And what's interesting about density is how can we measure the density of some objects if we can't get the volume. Obviously with a liquid, we can put it and measure it. We can measure the volume of a liquid. But how do I get the volume of an oddly shaped rock or a stone even? Well, we have this thing, a practical you can do. It's called a Eureka Con. And if you look at this setup, I have a measuring cylinder. Okay, so that's going to measure the volume of any liquid. So if I have this Eureka Con filled with water, and I take this object, oddly shaped object, and I dip it down in the water, the amount of water that's going to be displaced will be equal to the volume of that object. Okay, because when I put that object down in the water is going to get pushed away, and it's going to come down out of this little chute here and fill up this measuring cylinder. And then whatever this measuring cylinder reads, if it's 30 milliliters cubed or more, that would be the volume of this object. Okay, so if there's another practical idea that they might discuss or bring up, or it might not be just like this, but if maybe they'll ask you, how can you find the density of an object? And this is just different ways that you can do that. The reason why it's called a Eureka Con, it goes back to Archimedes. I think it's Archimedes. Yeah, pretty sure. Greek times, Archimedes. Anyways, the king needed to know if his crown was actually pure gold. So if they knew the density of certain objects or density of water, what they did was Archimedes was sitting in his tub, And when he sat in the tub, he noticed all the water came up and poured over the sides. So then he thought to himself, he could find the density of the crown by dipping in water and measuring how much water poured over the sides. And that's where you get that old story where he jumps out and goes, Eureka! It's true, I'm not lying. Okay, we're going to talk...
Wikipedia just confirmed it.
Wikipedia just confirmed it, alright. My credibility is still intact. Alright, so we're actually going to talk about change of state. And I'm going to do latent heat, okay, the same time I do change of state, because they go together. When I think about it, I think of them together. So a change of state is when we turn substances from solid to liquid to gas, or it could be in reverse. So gas to liquid to solid. So if we look at this diagram here, we have solid water, okay? And in scientific terms, I call that ice, okay? So we have ice. As you start to heat it up, okay, the ice begins to melt. And it's this area in here where if you look, so we're heating it up, the ice begins to melt as it's taking in heat energy, it begins to melt. But look, you would think the temperature will keep increasing, but it doesn't, okay? So it'll actually level off until all the ice is melted. Okay? And this is called the latent heat, right here. So until that all that ice is melted, you got this latent heat period, and when it gets to the point of how much heat is needed until it starts to change state. So now as you see, it starts to turn to a liquid, so this is where it starts to melt. So we get this latent heat where it finally becomes a liquid, and then it takes this much, it's water, takes 100 degrees, and we get this latent period again. So this will stay at this temperature now until all the water has become a vapor. And that's how I connect the two. Change of state and latent heat. The latent heat is the period it takes for all of the substance to change its state. And now that's the latent heat period. So like I said, you'll have these slides, hopefully they'll be uploaded, and you can take them and look at them and have a look at this. Next thing, particles. We talk about gas, we talk about gas pressure. When you fill up an object, okay, so if I had a balloon, which I don't, probably should have had one. If I had a balloon, I would start to blow it up, and what I'm doing is, I'm actually adding particles into that balloon. Now when I put the particles in that balloon, they're not just staying in place. Okay, they're moving. And as they're moving, they're hitting the sides of the balloon. And that's the pressure. And that's the pressure that we feel. Now, if I added, so talking about heat again, okay, because as we transfer energy into this balloon, okay, it's heating up, the energy is transferred into the particles, and they're going to start to move much faster. So they start moving much faster, they're going to hit the walls much more frequently. And that's how we're going to feel that increase in pressure. So we're adding energy to the particles move faster, they're hitting the walls more, and you get that pressure. Okay? That's the air pressure that you feel. So we're going to move on, and we're going to talk about discovery of atomic structure. Now, what's great about this is I believe Mr. Cave has already touched on this exact very thing in the chemistry. Talking about Rutherford and his gold foil experiment. So in the gold foil experiment, if you can remember, it was an alpha particle that they'd fire at this thin sheet of gold foil. Okay? Some of the particles went straight through, some deflected off a little, and some actually came right back. And that's how they started thinking, Rutherford discovered that the electrons were actually floating around there's space around the nucleus, and the alpha particles were actually bouncing off the positive nucleus and firing back, reflecting back at him. So he knew that an atom had to have a center, and the electrons had to be somewhere on the outside. A lot of space outside. So talking about that alpha particle, we're kind of moving into alpha decay. So it's a type of radioactive decay, which you need to know. And it's when the nucleus, so the nucleus of this atom, it loses 2 protons and 2 neutrons. And this is called an alpha particle. Alright, so when it loses 2 protons and 2 neutrons, it's an alpha particle. And when an unstable nucleus emits an alpha particle, its atomic number is going to go down by 2. And its mass number is going to go down by 4. So if we look at americium, we have a mass of 241, has atomic number of 95. Now, if it goes through alpha decay, okay, so that alpha particle just emitted, it now becomes neptunium because its mass number went down by 4. Its proton number, atomic number, went down by 2. So you're left with neptunium plus this helium, so the alpha particle. Mass of 4, atomic number of 2. And this is a nuclear equation. So important thing. So remember, if you know what an alpha particle is, so try to remember alpha decay, where it's mass of 4, decrease, and a decrease of 2 in atomic number. Whatever they give you, you know. Bring the mass down by 4, bring the atomic number down by 2. And then you add, make sure you still represent that an alpha particle is left at. And what's interesting, if you noticed, since we changed the atomic number, okay, we're changing the type of element. The other type of radioactive decay, okay, is beta decay. It's when a neutron changes into a proton. Okay, so we have neutrons and protons in the nucleus. And when that neutron changes into a proton, an electron is also emitted. It's created and emitted. And it fires out at a massive speed. So we have carbon. Neutron turned into proton. You see this little electron just went flying here. And what's going to happen is, since we're actually gaining a proton, because the neutron's turning into a proton, carbon has now become nitrogen. Okay, so the neutron has become a proton, so you're actually increasing the number of protons, and that makes it a new element. So we're left with nitrogen, and then the beta particle, which is then just 1 electron. So that electron comes firing out. This is also a nuclear equation, so you could get one or the other. So you just need to remember, or try to remember, which one is which. So alpha is minus 4 on the mass, 2 on the atomic number, and beta, you actually just increase the protons by 1. And then the other type of radiation is gamma radiation. It's actually a wave. Okay, so it's a form. It's not a particle. It's an electromagnetic wave, and it's emitted when an atom goes through alpha or beta decay. So it happens both during both types of decay. It has no charge or mass. So it's just an electromagnetic wave that gets emitted when alpha or beta decay happens. So when you look at these slides, we got types of radiation. This is a summary of all of it. So you can look at this table and make your notes on that. So you'll have these slides at home, so I'm not going to read this table out to you. Next we're going to talk about half-life. Okay, so what a half-life is the decay of radioactive isotopes, and it can be used to measure a material's age. So the half-life of an atom is the time taken for half of the radioactive isotopes in a sample to decay. Okay, so if you might see it in like this, like a graph, in a half-life graph. You'll have your counts per minute here. So this one on this graph, you'll see when you see it. Hopefully you have the slides at home. We got an 80 here, and what we're going to do is go down in halves. So half of 80 would be 40. And I would come over then to the line and then draw another line straight down. And that tells me the time it would take for 1/2. Then again, 20. And I would come over and draw my line down, and I'd find out half-life. And you can keep doing that. And as you can see, if I could draw it on this, which I don't have it working right now, it's 2. So every 2 days, it's gone down essentially by half, and that's the graph. You guys can try this at home. Hopefully you've been practicing this all the time. But, okay, so that's as far as I got for all of P1. So now, I think Sir has some things he'd like to say, actually.
Right. Thank you for that, Mr. Pritchard.
Cheers.
We've got a few questions coming in. I'll go through a few bits. We've got a bit of time, so I'll go through a few sort of examples of calculations and things like that that we may actually get. Some people are asking about the equations that we may have. So, just looking at those. Equation sheet you'll be given will look a bit like this. This is from the specification. You can actually download this yourself if you wish. But this is the equation sheet you'll be given. There are 7 ones that are given to you. Not all of these are used in P1. Some of them are. Some of the calculations you may need. So Mr. Pritchard talked about the change in thermal energy, which is already on there. Elastic potential energy, which is on there. So some of them are actually given to you already. You don't need to memorise. But there are actually 21 that you've got to memorise, and those 21 again, not all of them are used in P1. Just to give you an idea of the ones that are, quickly run through some of them. I might just zoom this in a little bit so we can see a little bit clearer and talk about some of the ones we need for P1. So we've got the weight equals mass times gravitational field strength, comes into forces, comes into a bit later on, so shouldn't need this. Work done equals force times distance. That's one that was mentioned, so that's definitely one you will need. Force applied to a spring, again we're talking about forces and this thing called Hooke's law, which will come up a bit later on in P2. Distance travelled, speed times time, point equation, but P2 for now. Same with acceleration, resultant force, momentum, so a lot of these are used. But when we get to the, actually come up in P2, it's when we get to the energy and electricity ones that we really need to think about some of these for P1. So the one for kinetic energy, which I always remember because you're actually given the one for elastic energy. Now the difference in elastic and kinetic energy is this is half mv squared, whereas elastic energy is actually just half me squared. So it's just switching of the E for the V. So if you've got that, if you you can look on the sheet for the elastic potential energy calculation, and just remember that for kinetic energy I'm literally just changing the extension for V, which is the velocity or speed of an object. Then I've got that calculation given to me, so that's a freebie that you can take by using the equation sheet. Gravitational potential energy, mass times gravitational field strength, G times the height. That's one that you need to memorise, and I'm going to go through a couple of sort of calculations you can get which are based around this sort of thing. These two are often linked together. They come up quite regularly, so we'll have a little look at that. Power. There's so many ways to calculate power, so many power equations, some for electrical power, some for general power when we're talking about energy. So power is energy transferred divided by time, or power is work done divided by time. Now they're kind of the same thing, because energy transferred is equal to work done, or work done is equal to energy transferred. Sir talked about lifting something up, doing work to lift it. When you actually got it there, you're holding it up, you're not doing work. But when you're lifting an object, you're transferring energy, therefore you're doing work. So work done is equal to energy transferred. So those two power equations are kind of the same thing. If you're given an energy, which you should know by now is measured in joules, that might be talking about the amount of work done, which is also joules because it's an energy. Then if you're given a time as well, divided by time, and you get the power in that transfer. Efficiency. So there's two for efficiency. They are essentially the same though. One using, again, energy, one using power. The power one is usually when you're talking about electrical and appliance. Efficiency can be any energy transfer. So for efficiency, the useful energy output, so that's the energy you want to get. Sir gave an example of a light bulb. And I was looking at this one. He had a Sankey diagram which had electrical energy in 100 joules and light energy out was, I believe, 75. So if that was the useful energy in, if I wanted the efficiency of that bulb, I would do the useful energy, which was 75 of light, divided by the total energy that went in, which was 100. Now efficiency can be given as a decimal, that would be 0.75. Sometimes they want efficiency as a percentage, and you should know by now to get anything to a percentage, you just do it times by 100 at the end. And in this case, because it's divided and times by 100, it actually works out as 75% efficient, that light bulb in the example. So that's efficiency from an energy standpoint. As I say, sometimes you'll be asked it from a power standpoint. So efficiency is the useful power output divided by the total power output. So if you've got an electrical device that's, let's say 1000 watts is actually the value on the device, but actually the useful energy that it's actually doing, so you might have to calculate the power output of a device, so the energy transferred over time to work out the power that it's actually being used correctly. So an electric drill or a hairdryer or something like that. The useful power output by that device would be divided by the total power of the device going in, and that would give you your efficiency. Again, you could times it by 100 to get it as a percentage. Look at what the question's asking you. But that being said, if you did do this calculation and forgot the times by 100, then you'd be pretty much most of the marks there already. You'd just be getting that extra last one at the end. And as I've said all through mine, generally if we're looking at a 3-mark question, if we're sort of getting 2 out of the 3, we're on for a good grade anyway. Obviously we want to maximise it, but let's score as many marks as we can. Wave speed is one that comes up when you do waves in P2, so not necessarily relevant for P1. But then we come on to the electricity ones, and these go off the page or to the next page. I'll come to it in a second. But charge flow, as said, so charge in coulombs is equal to the current in amps multiplied by the time. And Sir did mention these are given weird symbols, so Q is the charge, I is the current, so do remember that. And I comes up a lot, current, that comes up in a number of the equations. Then you've got several more, including 2 more for power. So this potential difference equals current times resistance. This V equals IR. That one is a really useful one for electrical circuits. One thing I'll mention while I'm on about this is something, a question that came in about rearranging this. So Miss Walker might have already replied, but just for everyone, with the equations we need to be able to rearrange them. Often these are the equations we learn, V equals IR, that's the one that you sort of memorise if you like, but the exams nowadays give you different things. They'll give you maybe the voltage and they'll give you the current and you'll need to know the resistance, or another way around, they'll give you the resistance and the voltage and you'll need to know the current. So you have to be able to rearrange them. When things are multiplied, now often when you see the letters just next to each other, they're actually multiplied together. If we want to take either one of these to the other side, to leave the one we want to find, we can take them round to the other side, and I always draw an arrow going under because they actually become divided by. So voltage divided by, or I should say potential difference divided by current is equal to resistance. That's one way I could do it. Where if I wanted the current, I'd be taking the resistance over to the other side and leaving I, and in which case it would be V divided by R equals current. Now, a couple of things about this, and something I've seen a lot in the papers so far, it seems to be a bit of the case, is being able to rearrange it is one thing, be careful with your units is the second thing. Often with these things, we have the units for potential difference in volts, we have the units for current in amps, and we have the units for resistance in ohms. But they might give you some of the units in say milliamps, so they might give you a very small current in milliamps. Now you need to be able to make those conversions. So a milliamp is a thousandth of an amp, so you need to be aware that you may need to do that conversion. If you're given something in milliamps and you want it in amps, you need to divide it by 1,000 to get it into amps, and make sure you do that first before doing your calculations. Similarly with watts, what they quite often do with power, we'll come to some of the power calculations, is you might be given a wattage in kilowatts. A kilowatt is 1,000 watts. So if you want to convert 1 kilowatt into watts, you have to multiply it by 1,000 to get a kilowatt into a watt. There are 1,000 watts in a kilowatt. So be aware of the units, take a look at the units, try to do that conversion. So as I said, there's two equations for power we've got here. So power is potential difference times current, P equals V times I, which is one Sir mentioned. And there's this other one as well, that power is equal to the current squared times R. Now that's something you can try and remember, or I like to know where things come from, because if you know where that comes from, you can actually work it out yourself, just by putting two equations together. It sounds more tricky than it actually is. We're going to use that equation I just had on the last thing, which is V equals IR. Okay, we remember that one from the previous page, okay, important for electrical circuits. But then also, if we take this one for power, where power is equal to the voltage multiplied by the current, if we just combine those two together, what essentially we are saying is, we're saying that the voltage is equal to the current times the resistance, and this is voltage times the current. So if we replace that voltage, because it's equal to the current times the resistance, with this equation, what we end up getting is P is equal to, so we're going to put in this instead of the V here, so this will be the current times the resistance times the current. And again, when we just put that together, that's I squared, because there's two of the I's in there, multiplied by R. So we can get that third equation for power using the V equals IR, and the power is voltage times current equation. We're just putting them together. That being said, I've told you where it came from. You don't necessarily need to know that if you just remember that another way to calculate power is the current squared multiplied by the resistance of the device that you're usually talking about, the resistance in the appliance that it might be referring to, or light bulb or something to that effect. So we've got energy transferred again, it's power multiplied by time, so we've got another one for energy transfer. Essentially though, that is just a rearrangement of the one, the power equation, where power is energy transferred divided by time. So although some of these are like, there's 21 equations to remember, some of them are just derived through each other, or just rearranged from each other. So they're essentially just using the same equation, but to do something else. An energy transferred is charge flow multiplied by potential difference. So the energy in joules is equal to the charge in coulombs multiplied by the potential difference in volts. And then last of all, density is mass divided by volume. So I mentioned it, density given the symbol sort of P, it's a bit of a weird P, equals the mass M divided by the volume. With that one, the thing I would say is be very careful with the units. That's one that might be critical of the units. They can give density in a few things. They can give you it in grams per centimetre cubed. You could get kilograms per centimetre cubed. You could technically get grams per decimetre cubed or kilograms per decimetre cubed. So have a look at your units, look at what the values you're given in the question are, and then try to make that conversion. I could go through them all, but in general what you've got to remember is kilo, like kilograms, is 1,000 grams. So remember that and make sure you can scale appropriately. One tip I give my students when it comes to conversion of units, think about what you're doing. If you've got a mass of 100 grams and they want the answer in kilograms, remember that a kilogram is bigger than a gram. So if I do it wrong, and I do, well, it's 100 grams times 1,000, I get 100,000 kilograms, alarm bells should ring in my head. They should say, well, that can't be right, because I can't have like 100 grams is actually equal to 100,000 kilograms. That doesn't make any sense. Okay, the kilograms is a bigger like quantity, so the value you get has to be smaller. So actually your 100 grams divided by 1,000 gives you 0.1 kilograms. Okay, if you're going from grams to kilograms or something to whatever, kilowatts, watts to kilowatts, the number should get smaller. And vice versa, if you're taking a number from kilograms to grams, that number needs to get bigger. In this case, you times it by 1,000. So think about what you're doing. Think carefully about what you're doing. Think about, does it logically make sense? Okay? The way the exams are designed now is they're designed to, yes, test your knowledge, yes, see what you've memorised over the course of your revision, but also they're testing whether you can apply that and whether you actually understand it and can use it. And the number one complaint I have about students in exams is when they rush through, they have a lot of time left over at the end. They maybe check their answers, which is good, do that. but then they've still got 10, 15 minutes at the end. Now this might not be you, you might be writing up to the last minute, and that's absolutely fine, because that's what we really want you to do. Okay, because if you've got through it early, maybe you haven't read all the information. Do read every single piece of information in the question, because some of the information is given to you, some of the answer may be given to you in an earlier part of the question, and if you haven't read it, you've just skipped down to where the answer is, you're going to have missed out on that. So that's just a bit of exam technique thrown in there as a free bonus, if you like. A few things as well I wanted to go over. Mr. Pritchard showed you a few of the circuit symbols. Let's see if we can go through all of them, because we may need to be able to recognise all the circuit symbols. So we'll just take it from the ones we need to know. We've got a cell, which is just one thing like that. And then we have a battery, which is multiple cells put together. So this is a battery. Now with that, generally, and Sir mentioned this, usually a standard cell is sort of 1.5 volts. So this might have a potential difference of 1.5 volts. If we had 3 of them in a battery, and we were told, you should be told that each of them has a voltage of 1.5, but if not, we might assume that anyway. If we had 3 of them in a battery, we would do 3 multiplied by 1.5 to get a voltage of 4.5 volts. So we can work out the voltage supplied by that battery by knowing the number of cells in it. Some other symbols, the common ones you come across, things like that, which is a bulb. Should recognise that, hopefully. Also, a switch. Now you could have a switch as open, or you could have a switch as closed. That's both versions of it. So we've got our switch there, which is shown, open and closed. Then to measure things, we've got a voltmeter and an ammeter, and I'll go into a little bit about these in a second, because this was a question that came in as well. So we've got a voltmeter and an ammeter, should be recognisable by the A or the V that's in it. Okay, so we've got those two. This one measures the current around the circuit, this one measures the voltage or potential difference. I should get used to using it. I always make that mistake myself in terms of not calling it potential difference, calling it voltage, but it's measured in volts, but it's actually potential difference. There's some common ones. We have some resistors we need to know as well that we'll go through. So we have our standard resistor, which is shown, which is like a rectangle with a line. This can be called a fixed resistor. Maybe, if you're given something like this, might have a resistance above it written, so like 20 ohms. Resistance, and we can potentially use that with some other information. If we knew the voltage or we knew the current, we could potentially work out the other one. We can have a variable resistor, which actually can alter the resistance or flow of electricity around a circuit, and that can be used to control the current that's flowing around a circuit, so ensuring you can do measurements. There's actually a practical you can do where you can vary the length of a wire in a circuit and attempt to measure the resistance as you increase the length of the wire, see if the resistance changes. So this is a variable resistor. One thing I mentioned, if you're doing experiments on circuits, and sometimes you'll get questions about it, it might ask you what you need to control. If you are measuring something to do with the resistance or the current, you need to ensure that the voltage remains constant. That could be the number of cells in the circuit, or if it's attached to a power supply, the potential difference of the power supply remains consistent. It could be something you can look for as a control variable. Also, if it's looking at resistors, as said, it needs to be kept at a constant temperature, or temperature needs to be ensured that it's constant. Some other resistors that were shown that you can have. Looks like a little tick for it, but it's actually a thermistor. And this is a resistor that changes its resistance based on the temperature that it's in. And I'm not sure if this symbol was shown, but another one you need to recognise, which is your LDR, which stands for light dependent resistor. Okay. The reason we can tell that's the light dependent resistor, and I'll come to another one that symbol's quite similar to this, is because it's got the resistor symbol in the centre. Most resistors have this symbol in there, and these arrows going in, they show the light going into it and affecting its resistance. So its resistance will change depending on whether it's in low light or high light. So if it's in high light, if it's in bright light I should say, the resistance will be quite low, and if it's in dim light the resistance will be high. Another one that you can get which is linked to these, which mentioned when he was talking about a plug, is actually one that looks like that, which is actually a fuse. This one, when I was going through this with my class, I actually neglected to put up there. I actually forgot myself till one of my students, Bobby Belsey, actually noted that I hadn't put this one on. She knew her circuit symbols very well, so she gave me the heads up on that. And she'll probably hate me if she watches this and I dropped her name in it. So. Shout out. There's a few others you may need to know as well. There is this one which looks like an arrow, which is the symbol for a diode. A diode is special because it only allows electricity to flow through in one direction, i.e. the direction of the arrow. So electricity will flow through in this direction. And then also linked to that is like a circle with the diode symbol in it, which stands for an LED. You've probably all heard of these. You've maybe got a TV with LEDs in it. You may have got certain devices with LEDs in it. But this stands for a light emitting diode. Light emitting. So this is used almost like a light bulb, but this is generally more efficient. Electricity can only flow through in one direction, and it's better at converting the electrical energy that goes into light energy, which it gives out. I use those terms. They're obviously energy transfers, as we should know, because the 7 energy stores is something we need to know, and light and electricity, they're kind of ways of energy being transferred rather than actual energies themselves in the new specification. So I'm still going to talk about it like that. Electrical energy in and light comes out, but that's energy being transferred from one thing to another, and they're stored in different ways. So there's some of the circuiting rules that we need to know and recognise. While we're talking about circuit symbols, I was going to talk about some examples of circuits and how you can measure certain things. So looking at a series circuit first of all. So if we have a series circuit, simple series circuit, and the reason you need to know circuit symbols is you could be asked to identify a certain device from the circuit symbol, or you could be asked to draw a simple circuit, so you need to know the symbols to be able to do that. If I'm going to draw a simple series circuit, I'm going to use, let's go for 3 cells in series with 2 identical bulbs. And the reason I say identical is because that affects some of the values that are given in this, what I'm going to talk about. So, if I wanted to measure the current around this circuit, I need to use an ammeter. Now, where does that ammeter go? You need to add the ammeter in series with the circuit. So I'm going to add it to the loop. Okay, I can't rub anything out, but I'm going to add it to my loop there. So that's where I could measure the current around this circuit. Now in series, it really doesn't matter where I add that ammeter, for the reasons Sir talked about, in the fact that current will be the same anywhere around that series circuit. So I could add it here, I could add it here, I could add it between the bulbs, over here, 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 anywhere I like, as long as it's in the loop, the current on that will be the same anywhere around the circuit. So I'm going to add it on the side over there. When adding a voltmeter to your circuit, you have to put the voltmeter across the appliance that you're measuring. So I'm going to measure the voltage across this bulb right here. So my voltage across that bulb is going to be measured by having my voltmeter across there. I could also measure the voltage across both bulbs or against the entire battery by putting it in different places. But look what the question's asking you if you want to put in a voltmeter to measure a certain device. These could be resistors, they could be another device. So when we take those measurements, as said, I'm just going to put some numbers to it to hopefully practically allow us to see. And some of them will be making up, to be honest. This has got 3 cells, so similar to the one I had before. This will be 4.5 volts of potential difference of electricity, if you like, that will be supplied by this battery. Saying electricity is not great, but like I say, we've got to let it slide for now. In terms of the current flowing around that circuit, and again I'm making this up, it wouldn't necessarily work, we would need to know the resistance of this, but we could maybe find it from a calculation, which I'll show you in a second, and this is application of the knowledge. I'm just going to make up the current for that ammeter, and I'm going to keep it nice and simple for myself. I'm going to say that has a current of 1 amp. Now, that current would be the same, as I said, anywhere I measure it. So if I had an ammeter anywhere on that circuit, the current would say 1 amp. Now the voltage. What voltage would I read across this bulb? One thing I mentioned, for those of you who are paying attention, I said these were identical bulbs. In a series circuit, if we're using identical resistors, a bulb is a type of resistor, remember, and if we're using identical resistors, the voltage or potential difference will be shared equally between the components if they are identical. If they're not, we could maybe calculate it. If we knew the reading here, we could work out the resistance of this. We could also work out the values for this, but that's a bit of a more involved process, and I'm not going to go exactly into it right now. As I say, we will be in tomorrow morning. If you want to know more about that, please do ask me. Anyway, in terms of this, they're identical bulbs. Because they're identical, they're going to share equally this potential difference. So the potential difference that this is going to read is 4.5 divided by 2, because there's 2 identical bulbs, which gives me 2.25 volts. That bulb is going to be receiving 2.25 volts of potential difference. Similarly with this, I'm not measuring it, but this would receive the same, because they're identical and the voltage is shared equally between them. Now, as I said, question could give me something like that. It could then go on to say, what would the potential difference be across these bulbs if I added a 3rd bulb or a 3rd resistor, it doesn't have to be a bulb, into this circuit? If it was an identical bulb, just like the 2 before, I would then have to take this voltage and split it 3 ways, in which case each bulb will be receiving 4.5 divided by 3, they'd be receiving 1.5 volts. And then if I had a 4th one, I'd have to do 4.5 divided by 4 to get, what would that be, 1.25, my maths has got 1.75, is that right? No, gone all over the place, but forget the actual calculation. Doing it in front of the camera always puts me off a little bit, but the actual value is not so important. It would just be that value divided by 4 if there was 4 in there, and so on and so forth. You could be asked about doing that. Right. So, what can we do with these values? We know now the voltage and the current flowing through this bulb, and we know a very important equation that links potential difference, current and resistance. We can work out the resistance of this bulb. The way we would do that is V equals IR. Now, we don't want V, we don't want, in this case, we want R, so if we rearrange it as I did before, R is equal to the voltage divided by the current. Just rearranging the formula, taking the I over to that side. So in this case, we put in our numbers, we know 2.25 is the voltage that's flowing through, or potential difference. The current, I gave myself an easy number, said was 1. 2.25 divided by 1 is 2.25. I can do that maths on camera. And it comes to 2.25 ohms. Okay, so once I've got some measurements, once I've worked out the voltage, I can then work out the resistance. So I'm applying my knowledge to a series circuit. Looking at parallel circuits, we're still going to have 3 cells. This time though, we're going to put in 2 bulbs in parallel. This time it would matter where we placed our ammeter. Again, we're talking about identical bulbs. If we put our ammeter over here, okay, and it was reading 1 amp, again using some easy numbers, keep it simple for myself. Over here, our ammeter would also be reading 1 amp. for the very good reason, as Sir said. The electricity would set out on its journey, half of the current would go one way, half will go the other, and when it gets to this point, when it returns to the battery, it would actually rejoin together and have 1 amp of current. But if I measured the current here and here, it would be 0.5 amps and 0.5 amps. It would be split evenly between the two parts, and that's because, as I said before, these are identical bulbs, so the current would be split evenly. If they were non-identical, again, I could possibly work it out if I have a resistor here and I knew the resistance of it using V equals IR, and then apply it to this if I knew the current going in. But that's a more involved question that I just don't have time to go over now. So again, see me in the morning if you want me to. So 4.5 volts, because I've still got 3 cells, all 1.5. 4.5 is 1.5 times 3. This time, the potential difference of these is very easy. They're identical bulbs, but that's kind of irrelevant in this case. They could be non-identical with the potential difference, because in parallel, the potential difference of each of the bulbs or each of the components is equal to that of the supply. So it didn't matter if I had 50 bulbs in parallel, they would all be receiving 4.5 volts of energy, or a potential difference I should say. So that's some work on series and parallel circuits. Sir told you about it. It's just a bit of application, putting a bit of numbers into it and seeing how we can maybe use V equals IR, because I could do it again. V equals IR. I know the current flowing through this bulb. I know the voltage. I could work out the resistance using resistance is voltage divided by current. I could find out. It would actually be a different resistance to these bulbs. Give it a try to the one that was on the previous question. So they must be different bulbs to what I used in the previous one, because they're different resistance values. Okay. So that's application of some of your circuits work. We've got probably about 10 minutes left. They'll go through hopefully just 2 things very quickly. One, as I say, used to be quite a common, I said when I was going through the equations, used to be quite a common question about conversion of gravitational potential energy into kinetic energy. Could be any object. Sometimes they use a diver, jumping off a diving board. It can be something different. In this case, we're just going to use a ball. And I'm going to make up numbers again for the sake of my calculation, but I'm going to use simple numbers to make it easy on myself, doing the mental maths right here in front of you live. So we've got the floor down there. This ball has a mass of 1 kilogram. Okay, so that ball has a mass of 1 kilogram, and it's actually lifted to a height of 2 meters off the ground. 2 meters off the ground. Okay. Now, what is, and this might be part A to a question, what is the gravitational potential energy stored in that ball at that point 2 meters off the ground? Okay, so remember my equations, I would know that GPE, or sometimes shown the symbol E with a little g by it, is equal to the mass times gravity times the height. Now gravity should be given to you in these calculations, and as Sir says, it's 9.8 is a value we often use. As I said, I'm going to be a bit cheeky on camera and just use 10 for the purpose of my calculation, but you've got to use whatever's given to you in the exam. If they give you the gravity as a value of 9.8, you need to use that in your calculations. But I'm trying to keep this simple for myself, so I'm going to use 10 as my value for gravity. So, mass is 1 kilogram, multiplied by gravity, which I said I'm going to use 10, multiplied by the height, which is 2 meters. Which tells me that if I do 1 times 10, that's 10, times 2 gives me 20. Okay? Gravitational potential energy is an energy, so therefore it's going to be measured in joules. If ever it's an energy unit, it's going to be joules. So that ball has 20 joules of energy stored in it at a height of 2 meters with a mass of 1 kilogram. That might be part A. Now part B might talk about if that ball is dropped, what happens to that ball? Well, obviously if that ball is dropped or let go, it's going to fall down. And when an object falls due to gravity, it's going to convert gravitational potential energy into kinetic energy, movement energy, because it's taken the potential it had up here, it's not moving anywhere, so it's got zero kinetic energy, but it's got gravitational potential energy at this height, and when I let it go, it's converting all of that energy into kinetic. Those transfers from kinetic to gravitational, gravitational to kinetic are quite common. They sometimes talk about roller coasters in these sort of things, going up, gaining gravitational, and down, gaining kinetic. But what they may ask you to do, and this is just purely something I've seen in past questions, might not come up at all, so don't base all of your revision tonight on this. And they might ask you to calculate the speed of that ball just before it hits the ground. So literally when it is less than millimetres above the ground. What we are assuming by that, we're assuming it's fallen the full height of 2 metres, okay, even though it would only do that when it touched the ground, but they say just before it hits the ground, that's what we're going to consider. It's converted all of its gravitational potential energy into kinetic energy. So at that point, right, just at that point, the gravitational potential energy that it had is equal to the kinetic energy it's now got, because it's converted all of its gravitational energy into kinetic. Sometimes you might get a question that why wouldn't that be true? Why wouldn't GPE equal exactly kinetic energy? And that's because energy is lost when an object moves due to friction usually. This will be feeling friction with the air particles it's falling through. If it's a roller coaster, it's simpler because it will be running on the rails, and friction with the rails will cause it to lose heat energy. But for the purpose of a question like this, you assume that all of its gravitational potential energy, 20 joules, has now been converted to kinetic energy, just at that point before it hits the ground. And what they sometimes ask you about this is they ask you what velocity is it travelling just before it hits the ground. Okay? Now I'm not necessarily going to be able to do this sum because there is a bit of a trick to it, but I'll show you how to work it out. Okay? So I remember my formula for kinetic energy, sometimes E with a little k rather than KE. I'm just old school, so I tend to write it that way. Either way, is half mv squared. Remember, v is the velocity or speed in P1 because velocity and speed come up more as scalar and vector quantities in Unit 2, in P2. Okay, so I've got my kinetic energy equation. Now I don't need to work out the kinetic energy because I don't know the velocity, but remember, all of my gravitational I just worked out in part A is now equal to the kinetic energy in part B. Okay, so I already know my kinetic energy. I want to get V. You can rearrange that. I'll go through how I rearrange it, but I'll just show you the equation in case you ever have to work out the velocity given the kinetic energy already. So the way I rearrange it is this is a half, which is also the same as putting it times by 0.5, or you could even put that as, this is exactly the same as mass times velocity squared over 2. That's essentially what I'm doing. So if I want to take this to the other side, I have to multiply kinetic energy by 2. Then if I want to take the mass to the other side, I have to divide it by the mass, and that will give me V squared. And then V squared, to get rid of that, I have to square root the answer. Now I've talked about a lot of steps in that rearranging. I'm not going to show them on here, partly for time, partly because I don't have the space, but I'm just going to show you how you work out the velocity. The velocity of that object is equal to 2 multiplied by the kinetic energy divided by the mass, and I need to find the square root of it. Okay? That's the actual formula for working out V. That looks incredibly complicated, but it's just rearranging this. I say just. I think kinetic energy is probably one of the most complicated equations you get in physics, one of them. Then I plug in my numbers. I know that the KE was equal to 20 because all of my gravitational potential was converted to kinetic. So this 20 has all been converted to kinetic. So 2 times 20. I hope this is not too low for you to see. When that object's dropped, does its mass change? Well, of course not. If you drop an object, it doesn't change its mass, so its mass is still 1. And then square rooted to find the velocity. So 2 times 20 is 40, divided by 1 is still 40. Anything divided by 1 is the same number. So I'm looking at the square root of 40 would be my velocity, which Mr. Pritchard looks like he's just about to tell me, because he's done it in his head, of course. He didn't use a calculator off camera.
6.32.
6.32. And the units for velocity or speed are meters per second. I apologise, it's very low there, but that's sometimes a question that comes up, converting gravitational to kinetic energy. It may not come up in the exam, but you still need to be able to use these formulas: kinetic energy, gravitational potential energy. In some ways, I hope it doesn't come up in the exam, because AQA will be knocking down my door saying, "How did you know?" But like I say, it's just something I've seen come up a few times, so I thought I'd go through one since we had the time to go through an example of that. It's an energy transfer from gravitational to kinetic energy in this case. Okay, right, we've got just 2 more minutes. I make it. I always like to make the most of the time. Miss Belsey, who's helping me, just stood up as if to turn off the camera, but I can't give up 2 minutes of time. That would be a waste, surely. You've paid for the full hour and a half. Are we getting paid for this? So I'm going to use those last 2 minutes to do one more thing. Mr. Pritchard showed you a half-life calculation using a graph. Sometimes you're given a half-life calculation just with data, just with some figures. You might be asked, if you start with, and again I'm making up numbers, trying to keep it easy for myself, 100 grams of a radioactive isotope, let's say uranium-235. So we'll say uranium-235. Right. Now there's a few ways this question can be asked. I might be given the half-life of it. So the symbol for half-life is T with a half. And I'm making up this half-life. It's not correct, but I'm just going to call it 1,000 years. Okay? So it takes 1,000 years for half of uranium-235 to decompose. If I started with 100 grams of uranium-235, and after a certain length of time I had 12.5 grams of uranium, how long has passed? Okay, that's what the question might be asking. So, what I have to do is look at how many half-lives have gone by. Okay, so in this case, well, is there a mistake on there?
No, she's going to work it out.
Oh, Miss Belsey's working it out, seeing if she can get there. We'll see if we can beat her to it. So, 100 grams. One half-life, it would drop to 50 grams. So that's one half-life that's passed. And I'm going to write by this T a half. Okay. Another half-life passes, and that 50 grams has fallen again by half to 25 grams. That's another T a half. Okay. And then finally, it drops by half again to make 12.5 grams. That's the actual decomposition that's gone through. So it's gone through 1, 2, 3 half-lives. Now this is quite a common mistake. Students will go, well, there's 4 numbers there. Half-lives 1,000 years, 4,000 years, right? That's the mistake to fall into. It's how many half-lives have passed. And there's actually 3 half-lives. There's 1, 2, 3 half-lives that have gone by. So 3 times the half-life, which is 1,000 years, tells me that from that to happen, it took 3,000 years for it to drop from 100 to 12.5. Now, the last thing I'm going to leave it on, the flip to this question is, they might give you, it's gone from 100 to 12.5 in 3,000 years, calculate the half-life. This time you have to work out how many half-lives have passed, just like I did then, and instead of doing it multiplied, because you don't know the half-life, you do 3,000 divided by 123 to say the half-life is 1,000 years. So that's 2 ways they can ask you about half-life given some data. They can ask you about it on the graph as well. Okay. That's all we've got time for. We've used our hour and a half now, so we're gonna end up, as I say, we'll be in tomorrow morning. Your exam's not till the afternoon, 1:30. Be around in the morning. Maybe if you haven't got a lesson in the morning, you've got a class, you can ask your teacher to put on the live stream. Even if you've watched it already, watch it again, see what you can recall. Practice your calculations, look for the data sheets. But all that's left for me to say is, well, I say good luck, but like I say, I don't really like it as a term, because if you've put in the work, then I'm sure you're going to do really well. And I'll see you after the exam. Otherwise, thanks for watching.